position and velocity as a function of time. If you cannot solve it analytically, you can just put it in a computer and the computer will solve it numerically. If you have, in quantum mechanics, again, if you know the potential, you have a differential equation which you just solve for your particle, for your initial conditions, and if you cannot solve it analytically, again, you put it in a computer, and the computer just solves it for you. If you have two particles, well, if the force between those two particles is only depends on their relative separation, let's say that if you have such a system that is described by such a Hamiltonian, this is a two-particle system. Whether you are doing the quantum mechanics of this system or classical mechanics, it doesn't really make too much of a difference. Basically, you define the relative coordinate, the center of mass coordinate, and in terms of these new coordinates, your Hamiltonian just becomes the kinetic energy of the center of mass plus the relative moment, the kinetic energy of relative motion. So again, you just separate this problem, you reduce it to a one-particle problem, and we know how to solve the one-particle problem. Even if we cannot solve it analytically, we can solve it numerically. So this is a two-particle system. There's an algorithmic way of solving them. Have you tried solving the three-particle problem? Basically, it doesn't have a solution, except in some special cases. I mean, we can only solve systems of one particles or system of two particles. And if we have more particles in our system, we basically take into account either the external potentials or two-particle potentials. We try to ignore or at most approximately calculate, let's say, the three or four-particle potentials. So because they are not things we can actually solve. Now, the systems that we will be actually interested in will have an Avogadro's number of particles. Not just one, not just two, not just three, but 10 to the power 23 particles. I mean, again, let's consider it classically, if you would like to solve this system of equations, we will not be able to solve it analytically. Even if you try to solve it, you say, even just the initial conditions, you will have 6n initial conditions, 3n positions, and 3n components of the momentum of each one of those particles. Those are 6n conditions, and when n is 10 to the power 23, I don't remember the exact number now, it's many terabytes of data, just storing the initial conditions. I'm not even talking about solving the differential equation. So it won't be practical. I mean, with the current technology, we cannot actually solve it. We have to simplify it. Now, simplifying it also means that what are we interested in? You see, in a single particle problem, if you are interested in, I don't know, the trajectory of planets, you just treat it as a single particle, and you would like to know the position and the velocity at each time, how it will change as a function of time, so you can follow its trajectory, velocity, etc. But if you have 10 to the power 23 particles, let's say, this is my keychain. If you would like to study this keychain, I don't really care about the position and velocity of each one of the atoms making my keychain. I don't care about them. There are just a few things that I really would like to know. So what would you like to know about my keychain?
Macroscopic properties.
Which are?
Mass.
I would like to know the mass. Essentially, will I be able to lift it up or not? Or if I put it in my pocket, will it just tear apart my pocket? That's something I would like to know. What else I would like to know?
Pressure.
Pressure, if it's a gas.
All of the physical observables.
Which are?
Thermodynamical.
Which are? Temperature. I would like to know the temperature. And I don't want to burn my hand.
Volume.
I would like to know the volume. Will it fit in my hand? I mean, I wouldn't try to pick up a keychain that won't fit in my hand.
Magnetization.
Well, will it interact with a magnet? If I have some magnets in my pocket, I would like to know if it will interact with it. Magnetization. And basically that's it. Maybe just you can just add a couple of more over there. You see, I don't want to know the position and velocity of 10 to the power 23 particles. I just want to know just a handful of properties. And this is some question that I can actually answer, that I can study them. So that will be our aim. So now, what is the difference between thermodynamics and statistical mechanics? Is on one hand, as some of you had pointed out, we have macroscopic properties. Like the mass, the volume, the temperature, the pressure, etc. What thermodynamics does is it tries to find relationships between macroscopic properties themselves. This is what thermodynamics does. Relates one macroscopic property to the other one. And of course, what I mean by macroscopic properties, I also include their derivatives. So how does the pressure change with volume or temperature? So the advantage of thermodynamics is if you find a relationship using thermodynamics, that relationship is valid for any system that you can imagine. It doesn't matter whether it's a key change or a sponge over here or a wooden table. Any thermodynamic relationship that you drive will be valid for every system. It's just some relationship between the various properties. Now, what statistical mechanics does is there is the microscopic properties. Like the 6n coordinates and momenta, the 6n components of coordinates and momenta of the particle, how the particle interacts. It tries to relate these microscopic properties to the macroscopic properties. And hopefully without solving the equation of motion for each one of those particles. Just starting from some general principles, can we relate the microscopic properties to the macroscopic properties? So that, for example, thermodynamics cannot relate, cannot start from the, cannot tell me why this is shiny. Okay, if I know other properties of this system, if then I can use thermodynamic properties to prove that, to show that this key change should be shiny. But first I have to determine other properties experimentally. Thermodynamics will relate macroscopic properties to other macroscopic properties. But statistical mechanics will start from the atomic principles and tell me that this should be shiny. Well, the nice thing is, of course, the statistical mechanics can deal with individual systems separately and try to explain their properties starting from the microscopic picture. But that also kind of makes it more difficult, and the results that you obtain will be valid only for that system. They need not be valid for other systems. So if you drive a property for the ideal gas, let's say, starting from microscopic properties, well, that property will be valid only for the ideal gas, but let's say it won't be valid for carbon dioxide gas. Now, today I would like to start with thermodynamics. In a moment, I'm hoping that it will be more clear, this distinction between statistical mechanics and thermodynamics. So do you remember the laws of thermodynamics? Or has it been too long? So let's start with the zeroth law. What zeroth law, well, thermodynamics, we will be dealing with systems in equilibrium, both in statistical mechanics and also in thermodynamics. It means that the systems will not be changing in time. The pressure will be uniform, the temperature will be uniform everywhere. So those are the systems that we will study. So what Zeroth law tells us is that if system A and B are in equilibrium with system C, then A and B are also in equilibrium with each other. Well, this law basically states that we can define a property of the system that we will call the temperature. There is a quantity called the temperature, and so if two systems have the same temperature, then they are in thermal equilibrium with each other. This is the, how does it tell me that it defines a quantity called temperature? Well, let's imagine many systems that are not in equilibrium with each other. And if you give me a system A, I can just look at with which of these systems it's in equilibrium with. Let's say that it's not in equilibrium with this one, not this one, but with this one. And then if I find another system B, if it's in equilibrium with this one, again, the Zeroth law tells me that A and B are in equilibrium with each other. So that's the statement. So what is C? I can just give it any name. I can call it AJ Mehmet, or I can call it 1 Kelvin, 2 Kelvin, 3 Kelvin. I can give it any name I want. So the only thing I need to do is to determine whether a third system is in equilibrium with A and D is just match it with one of these systems. If it is in equilibrium with this one, I will say that, let's just say that this has a name. Let me call that 1D, 1L. What is L? I just made it up. You can also use Fahrenheit, you can use Kelvin, whichever one you want. If this is in equilibrium with this one, I will also call this system as 1L. It has the same property. And if I find systems that have this property as 1L, they will all be in equilibrium. And this property 1L is what I call the temperature. Of course, we don't use this 1L or 2L, etc. We have the Kelvin temperature, Celsius temperature, but at least the Zeroth law tells me that there is such a property that I will call the temperature. Now, the first law. Now, we will look at the changes in a given system. U will be the internal energy. Now, the first law states that the internal energy of my system, the internal energy can increase or decrease. Let's say if the system does work on some other system, then the internal energy of my system will decrease. If I do work on my system, let's say if I compress it, I'm doing work on the system, so the internal energy will increase. So delta U is, the sign convention is delta W is the work done by the system, and hence the minus sign. If the system does work, then the internal energy of the system is decreasing. If I am doing work on the system, that basically means that the system doing negative work on me, in that case, the internal energy of the system will be increasing. And there might be other factors changing the internal energy of the system, which we all call the heat, Q, heat. For example, when you rub your hand, you are basically creating heat. You are increasing the internal energy of your hand by giving it heat. Now, just a warning. It kind of seems trivial that, okay, if the energy is changing, it's either the system is either doing work or we are giving energy to it. But a couple of things that you have to pay attention to. You see, this delta symbol we usually use to denote changes in a quantity. But delta W is not the change in any quantity. There is no function W whose change gives us delta W. It just doesn't exist, such a function. Similarly, delta Q is not the change in anything. In fact, if you have a given system, you can change the state of your system from an initial state to a final state in different ways. And in each one of these ways, delta Q and delta W might be different. There's a huge but over here. Delta U, this is the change in the internal energy. U. And most of the time we will calculate that, we will be able to calculate delta W and delta Q by the changes in the macroscopic properties of the system. So this also tells me that I can express U, the internal energy of the system, in terms of the macroscopic properties of my system. So if I know the volume, the pressure, temperature, etc. of my system, that will allow me to calculate delta U. And hence, it will allow me to calculate U. I will be able to express the internal energy in terms of these quantities. Any questions up to here? Now, most of the time we will look at changes which will still keep my system in equilibrium. So we will be doing changes slowly at small steps. In such a case, let's say that this is my system at a given time. Let's try to express this delta W, delta W and delta Q in terms of other properties. Well, let's say this is my system at a given time. At a later time, it expands, or it can even contract. So different parts of the surface will move in different directions. Let me just pick up one segment here. Let's say that after my system expands, changes shape, this surface becomes this surface. This is the R. Well, the work done will be just F dot dr. Well, the force will be pressure times the area. The area element. This is my dA. Area times R, this is nothing but dV. So the work done by an expansion of my system You see, of course, this is the work done due to the displacement of a very small area element. If you would like to calculate the work done by all the if you sum all the area elements, then this will be P times dV, where dV is the change, all change, total change in the volume during this very small expansion. So the work done by the system will be P times dV. Well, it's usually a good idea to check the signs. You see, if the system is expanding, it means the system is doing work on the environment. Then dV is positive, P is positive, so dW is positive. So the sign here is the correct sign. So du will be minus P dV plus dq. Now this sign dq, this bar, to signify that this is not the differential of Q. It's not the differential of Q for the simple reason that there is no Q. There is no function Q. So this already, for example, allows us to study certain things, certain systems. We'll be, as I said, dealing quite frequently with the ideal gas. Well, the ideal gas law relates pressure, volume, and the temperature of the gas. PV is equal to nKT. N is the number of particles. K is the Boltzmann constant. T is the absolute temperature. P is pressure, V is the volume of the gas. So what does this tell me? Let's say that, okay, so there is another U is equal to N3 over 2 nKT. This is U is the internal energy. So these properties of the ideal gas, we will derive them later on. But let's just use them for the time being. Let's say that we look at a system of T is equal to constant. And let's say that we have an ideal gas a piston with an ideal gas inside. Initially it has a volume V1, it is at a temperature T. And let's say that we let this gas expand. This is the PV diagram. So initially it is at a volume V1. I let it expand at constant temperature. So that tells me that PV is constant for this process. If PV is constant as I change the volume, the pressure drops inversely. So this will be how the pressure changes as I change the volume. So let's say that eventually I reach the volume V2. Now I can calculate how much work the system has done. So the work done, the total work done, will be just the integral of the work done at each step. Well, I can imagine this process as small steps. At each step, the pressure will be P as a function of V. The volume will change by dV. Well, the pressure is N times K times T over V. The volume changes from V1 to V2. So this is nKT times logarithm of V2 over V1. The work done in this so-called isothermal expansion, from V2 to V1 is given by this expression over here. Now, what is the change in the temperature of this system, in the internal energy of this system? Remember, U is 3 over 2 nkt, n is fixed, k is just a Boltzmann constant, it's a constant, delta U is 3 over 2 nk delta T. But we are told that we are looking at an isothermal process. So basically, T doesn't change. Isothermal means the temperature doesn't change. So this is just 0. But the first law of thermodynamics tells me that delta U should be equal to minus the work done by the system, which is minus nkt logarithm of V2 over V1, plus the heat given to the system. So now we know how much heat is given to the system. You see, as the system is doing work, if you just imagine the pressure as just collision of particles with the boundaries, during the collisions, as the system is expanding, doing work on something else, that means the system is transferring energy on something else. So if we don't do anything else, if we just let the system, isolated system expand, it should lose energy, which means its temperature should drop. But we said that we are looking at an isothermal process. So to be able to make sure that this process is isothermal, we have to give energy to the system so that its temperature doesn't drop or its internal energy doesn't drop. So we are giving energy to the system as the system is expanding. We are giving energy in such a way that the temperature of the system stays the same. That is how we create the isothermal process. Well, in practice, what we do is we just take a large oven or a heater, the so-called heat reservoir, we have a heat reservoir, and our piston is in contact with this heat reservoir. As it expands, it takes heat from this heat reservoir. So it takes heat, some amount of heat from the reservoir, and does work in such a way that its internal energy stays constant. Well, there is another important process for the ideal gas, so, well, in general, let's say, an adiabatic process. Well, in an adiabatic process, delta Q is 0. Well, we will see a more precise definition of an adiabatic process rather than just delta Q is equal to 0. Well, the system should be isolated. There is no heat exchange with the environment. But at the same time, any change in the system should also be very slow. Let's say in the case example of the piston, let's say if we isolate the piston and we just hit the piston very fast, what will happen is we will create a shock wave in the gas. That will generate heat. So delta Q will not, although delta Q is not taken from outside, you are generating heat by that shock wave. So you should avoid that if you want to look at an adiabatic process. So you should compress or let the gas expand slowly. Now, slowly, but if you are too slow, you should also be careful about that. No isolation is perfect. If you are too slow, during the expansion, there will be significant amount of heat exchange with the environment, so that's also not something you want. You want to be fast enough so that there won't be any heat exchange with the environment, but nevertheless slow enough so that you are not creating any shock waves or anything similar. That is what's an adiabatic process. For the ideal gas, during an adiabatic change, PV to the gamma is constant, gamma being some constant. Well, again, if you know the you just follow, you can follow exactly the same steps to calculate the work done. There's no heat exchange, but then you know how much internal energy change. You can calculate the internal energy by basically following exactly the same steps, but this PV will have a different form. P0, V0 to the gamma, whatever the initial pressure and the volume is during this adiabatic change, it will be the same throughout the process. Of course, the temperature of the system will also change. If the system is doing work, it basically means that it is converting its internal energy to external work, and hence its internal energy should decrease, so the temperature should decrease. So we have these two processes. Using these two processes, we can actually devise what is called a Carnot cycle or a Carnot engine. You see, this gamma is larger than 1, by the way. Now, what is a Carnot engine? Let's say we have two heat reservoirs, T1 and T2. Let me just take T1 to be larger than T2. I take my ideal gas piston filled with ideal gas. I let it expand. So during this time, it takes some heat from the so-called hot reservoir. Then I isolate it after some time. I let it during this time, its temperature is T1. I let it expand in this isolated mode in an adiabatic process. This is isothermal. This is adiabatic. Until the temperature, well, you see, in an adiabatic expansion, the temperature drops. So you see here, as the piston is expanding, it is doing work. Here, during this adiabatic expansion, it is all still doing work. Since it's isolated, its temperature is dropping. Once the temperature reaches T2, I bring it back, put it in contact with the reservoir at low temperature. I keep compressing it. Again, this is isothermal because it's in contact with a heat reservoir. So it releases some heat, Q2, to the cold reservoir. After some time, after some compression, once its volume reaches some specific value, I again isolate it. But now it's cold. I keep heating it. I want to heat it before putting it in contact with the heat reservoir. So I keep compressing it. So now I am doing work on my system. The work that I am doing is being stored as the internal energy of my gas. So the internal energy of my gas is increasing. Well, that means the temperature is increasing. So at this stage, temperature is increasing. Here the temperature was dropping. So when temperature reaches the temperature T1, the temperature of the hot reservoir, I can repeat the cycle over again. So now this is a cyclic process. And at the end of the first cycle, at the end of every cycle, my piston basically comes back to its initial state. All the macroscopic properties are the same. So during this process, what happened is it took a Q1 amount of heat from the hot reservoir. Some of it is dumped into the cold reservoir, and the difference is used to do some work, useful work. So this is the basic, well, this is in fact the most, as we will see, this is the most efficient heat engine that you can devise. It converts heat energy into work useful heat. So if I would draw the PV diagram for this process, let's say at the first stage, you see at the first stage, it is at a high temperature and small volume. So its pressure should be high. So I start with a high pressure, let's say this is P0, and small volume. Then I let it expand isothermally. So in an isothermal process, PV is constant. So this is the isothermal expansion. Once it reaches, let's say, the volume V1 at the pressure P1, now I'm at the second stage. Now, in the second stage, I let it expand. I allow it to keep expanding. But now this is an adiabatic expansion, so its temperature is also dropping. In an adiabatic expansion, PV to the gamma is constant. Gamma is larger than 1, so it is dropping faster now during this adiabatic process. Let's say this is at T1. And now the volume is at V2, pressure is at P2. It has a large volume, a small temperature, so the pressure is really low. Now I reach the third stage of my engine. Its now temperature is now T2, I'm compressing it isothermally. This is again PV is equal to constant. This is at temperature T2. And it reaches volume V3 and pressure P3. And the final stage is an adiabatic compression. I need to heat it up. So this is again adiabatic. Now, if you would like to have a closed cycle, and that's what you would like to have, you cannot have these V0, V1, V2, V3 arbitrary volumes. They have to be related somehow. Well, we know that P0, V0 is NKT1, which is the same as P1, V1. Now, P2, V2, which is NKT2, it should be equal to also P2, V2. And furthermore, we know that P1, V1 to the gamma, should be equal to P2, V2 to the gamma. Here, at this point, I have P1, V1 to the gamma. And this point, they are both at the same adiabatic curve, so PV to the gamma should be the same at the beginning and at the end of that curve. The same thing will hold for, let me give them names, A, B, C, and D. Between the point D and A, they're on the same adiabatic curve, so P3, V3 to the gamma should be equal to P0, V0 to the gamma. And in particular, if I divide them side by side, it should still be the same. So I have P1 V1 times V1 to the gamma minus 1 divided by P0 V0, V0 to the gamma minus 1 should be equal to P2 V2, V2 to the gamma minus 1, P3 V3, V3 to the gamma minus 1. I just factor out 1V and wrote the remaining. Now, why did I do that? Well, look at this relation. Since P0 and V, the point A and B, they're at the same isothermal curve, P0 V0 is equal to P1 V1, and P2 V2 is equal to P3 V3. So I can cancel those things, which basically tells me that the volumes should be such that V1 over V0 should be equal to V2 over V3. Now, these are all isothermal processes, adiabatic processes. We had already seen how to calculate the work done by the system, the heat taken or given to the system during an isothermal process here. You can basically study it in all of these processes. So the system will take heat, Q1, as it goes from A to B, and release heat, let's say Q2, as it goes from C to D. In fact, we can just write them down straight away. You see, Q1 is this one. You see, this is nKT times logarithm of the final volume to the initial volume. This is how much heat the system has taken. So Q1 will be nK. From A to B, the system is at the temperature T1. And the volume change from V0 to V1. And Q2 is nKT2. And the change in the volume is V2 over V3. Well, you see, Q1 and Q2 are not the heat given to the system. Q1 is the heat given to the system. Q2 is the heat that the system gave away. So that's why the volumes, the ratio of the volumes is not always the last volume minus the initial volume. There's a sign difference between those two. Well, now we have an interesting result though.
Isn't it V3 over V2 in the second order?
Hmm?
The final volume is V3, right? In the
Yes. But you see, minus Q2 is the heat given to the system. So minus Q2 will be nKT2 times logarithm of the final volume over the initial volume. I just moved that minus sign to the other side. But you see, if I take the ratio, Q1 over Q2, you see V1 over V0 and V2 over V3, they are the same. So the logarithms cancel. The number is fixed and K is just Boltzmann constant. So Q1 over Q2 is T1 over T2. Well, the work done by the system will be, you see, Q1 is the heat taken by my engine. Q2 is given back to the environment. So the difference is the work done. The efficiency of such an engine is basically how much work you can get from the energy you give to the system. So the efficiency in this case will be omega over Q1 or 1 minus Q2 over Q1 or 1 minus T2 over T1. Remember, T2 is the cold temperature, T1 is the hot temperature. So the maximum efficiency depends on the ratio of the temperatures. And it is less than 1. Now let's give a break over here. In the second hour, I will pick up from this one. I will essentially write it in a slightly different form. Q1 over T1 minus Q2 over T2, this is equal to 0. And from this one, we will obtain the second law of thermodynamics. So any questions before we go for a break? So see you in 10 minutes.